Let's see the question. For the BJT Q1 in the circuit shown below, beta is infinite. VB on is 0. 0.7 volts. VC saturation is 0. 0.7 volts. The switch is initially closed. At time t is equals to 0, the switch is opened. The time t taken at which the Q1 leaves the active region is. So let's see the circuit first. This is the transistor circuits. VCC is 5 volts and there is a current source here 0.5 milliamperes, and there is a transistor. Here the base voltage is given as minus 5 volts. This is the NPN transistor. The emitter resistor is given as 4.3 kilo ohms. And here this is minus 10 volts. VEE. VEE is minus 10 volts. Here there is a branch. There is a switch here. Okay. And there is a capacitor across the switch, that is 5 microfarads. So they are saying that the switch is closed. Initially, the switch is closed. And when the switch is closed, the entire current flows through this short circuit. Because this acts like a short circuit, the entire current flows in that path and the transistor will be in off condition. So when switch is closed, that is at t less than 0, the transistor will be off. Transistor Q1, this is transistor Q1. Q1 is in off condition. At t is equals to 0, the switch remains open. So at t is equals to 0, the switch across the transistor remains open. Okay, this is at t is equals to 0. The current flowing is 0.5 milliamperes in the collector. So now, when the switch is open, when switch is open at t is equals to 0, the Q1 becomes on and it remains in active region. Q1 remains on. Now, at this instant, the Q1 is on. So, if you apply the Kirchhoff voltage law in the input loop by applying KVL, by applying KVL at the input loop, by applying KVL at the input loop, you will get VBB is equals to VB base emitter voltage plus VE, that is a voltage drop across the emitter, that can be also written as IE emitter current and emitter resistor plus VEE. So by substituting the values, you will get minus 5 is equals to VBE is given as 0.7 volts. The emitter current is not known. Emitter resistance is 4.3 kilo ohms. And VEE is nothing but minus 10 volts. This gives emitter current IE as 1 milliamp. So now the emitter current is 1 milliamp. So with this, we can write as the beta is given as here beta is given as infinite. This makes IB approximately close to 0, which can be negligible. So the emitter current and collector current both will be same. So the collector current flowing in the circuit, flowing in the transistor is also 1 milliamp. So when the collector current is 1 milliamp, if you apply the KCL at this node, at the collector node, this is 0.5 milliamps, and the remaining 0.5 milliamps come from the capacitor. Okay, the capacitor discharges in this way. So if you name this current as I1, you will get the collector current is equals to 0.5 milliamps plus I1. You can write I1 as 0.5 milliamps, which is nothing but the current, discharging current from the capacitor. Discharging current from capacitor. So there will be certain voltage across the capacitor. If the capacitor is discharging the current in the sense, what is, there will be some voltage across the capacitor, that is VC. We need to find out that VC. So by applying the Kirchhoff voltage law in the output loop like this, by applying the Kirchhoff voltage law, by applying KVL in the output loop, you will get the voltage across the capacitor VC is equals to VCE saturation, that is a collector to emitter voltage, plus VE, that is a emitter voltage drop across the emitter resistance, which can also be written as IE into RE. So by substituting these values, this is 0.7 volts, and there is one more voltage, that is nothing but VEE. Okay, so this is 0.7 volts. The emitter current is 1 milliamp. The emitter resistor is 4.3 kilo ohms. VEE is nothing but minus 10 volts. So the capacitor voltage is nothing but minus 5 volts. That is the voltage across capacitor. So this you can write as this: at a time t is equals to 0, the switch is open. So the current flows till the time period t1. The charge across the capacitor can be written as capacitance voltage across the capacitor, which is also equal to the current flowing I1 into the time interval 0 minus t1. So at t is equals to 0 instant, the switch is open. So the current flows till the time interval t1. So 0 minus t1. So if you substitute these values, the Q value will be minus 25 into 10 to the power of minus 6, because the capacitance value is 5 microfarads and the voltage across capacitance is minus 5 volts, is equals to the current I1 is 0.5 milliamps minus t1. So the t1 interval is nothing but the time taken by the transistor to leave the active region is nothing but 50 milliseconds. So answer is option C. We'll see the next question. In the circuit shown below, the capacitors C1 and C2 are very large, and the shorts at the input frequency Vi is a small input. The gain magnitude V0 by Vi at 10 into 10 to the power of 6. This is 10 into 10 to the power of 6. 10 mega radians per second is. So he's asking about the gain, whether it will be maximum, unity, minimum, or 0. So basically, if you see, this is a parallel resonant tank circuit. For the parallel resonant tank circuit, this is the inductor, capacitor, and resistor, R, L, and C. This is the parallel resonant tank circuit. The graph will be like this. The impedance graph will be like this. This is Z impedance and this is a frequency F. So the impedance keeps on increasing in the first half and it reaches the maximum point at the resonant frequency. And it reduces, come back to lower values at the higher frequencies. So at the lower frequencies and higher frequencies, the impedance is minimum. At the resonant frequency, the impedance is maximum, that is ZP. Okay. So now here we need to find out the voltage gain of this particular circuit. Like the video, share the video, and subscribe to the channel for better content and more videos. So for the parallel resonant circuit, at the resonant frequency, the impedance is maximum. Okay. So if you see the AC equivalent, the load impedance ZL can be written as ZP, that is the impedance of the parallel resonant circuit, is in parallel with the load resistance RL. So the output voltage is nothing but the output current, IC, collector current, multiplied with ZL. But here, ZL can be approximately given as load resistance RL, because the ZP, the impedance of the parallel resonant circuit, is very, very high at resonant frequency. What is the resonant frequency here? The resonant frequency is nothing but FR is equals to 1 by 2 pi root over LC. So the inductor value is given as 10 microhenries and capacitor value is given as 1 nanofarads. If you substitute those values, you will get the answer approximately equal to 10 mega radians per second. So here he is asking for radians per second. So this 2 pi should not be considered. Okay. Radians per second in the sense the 2 pi will come here. You have to calculate omega r. If you calculate this, it will be 10 mega radians per second. So circuit is at the resonant frequency. So output can be given as the collector current multiplied with RL. So here ZP is maximum. So there is a maximum output. You can tell that ZP is at the maximum value. Hence, the output voltage is also maximum. As the impedance is maximum, the output voltage also will be maximum. As the output voltage is maximum, the voltage gain V naught by Vi is also maximum. The voltage gain will be minimum when at the lower and very high frequencies. This is the lower frequency range, and this is the very high frequency range where the gain is very low. At the resonant frequency, gain will be high. So answer is option A, maximum. We'll see the next question. For the BJT in the amplifier shown below, VBE is the base emitter voltage is 0.7 volts. The thermal equivalent voltage, that is the base emitter voltage, thermal equivalent voltage is 26 millivolts. Assume the BJT output resistance R0 is very high and the base current is negligible. So the capacitors are also assumed to be short circuited at signal frequencies. The input voltage Vi is directly coupled. The low frequency gain of the amplifier is. So it's very simple. He has given the base emitter voltage as 0.7 volts. The thermal equivalent voltage Vt is 26 millivolts. And IB is negligible. That means beta is infinity. IB is negligible, approximately equal to 0, which also indicates the collector current is equal to emitter current. And he is asking us to find out the low frequency gain. Okay, so we'll try to find out the emitter current by applying the Kirchhoff voltage law at the input loop. By applying KVL, Kirchhoff voltage law at the input loop on DC conditions. Okay, so in the DC conditions, AC sources will not be considered. They will be considered as a short circuits. Okay, so by applying KVL at the input loop on the DC conditions, we will get VBE, base to emitter voltage, here plus and minus, and voltage across the emitter resistance, VBE plus VE emitter voltage plus VEE is equals to 0. So VBE is 0.7 volts. Emitter voltage can be written as emitter current, which is unknown, and multiplied by emitter resistance, that is 20 kilo ohms, plus VEE, which is nothing but minus 10 volts. So from this, you will get the emitter current IE as 0.465 milliamps. So that is the emitter current. Now the transconductance, if you see, because he has given the parameter thermal equivalent voltage, so we can calculate the transconductance. GM is equals to output current IC divided by thermal equivalent voltage. The collector current and emitter current can be same because beta value is given as infinity. Base current is negligible. So 0.465 milliamps divided by 26 millivolts. So you will get the transconductance GM value as 17.88 milliampere per volt. So once the transconductance value is derived, you can easily find out the voltage gain. The voltage gain AV can also be written as GM multiplied by load resistance R dash L. Why? Because GM is nothing but the output collector current multiplied by output load resistance divided by input thermal equivalent voltage Vt. So it can be written. So here R dash L is nothing but the collector resistance in parallel with the load resistance, which is nothing but here 10 kilo ohms in parallel with 10 kilo ohms, which is 5 kilo ohms. So substitute the values. The voltage gain is equals to 17.88 milliamps per volt multiplied by 5 kilo ohms, which will be equal to minus 89.42. Why there is a minus here? Because there is a 180-degree phase shift in the input and output currents, output voltages. That's why minus. So the answer is option D. Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.